NCBM 0324, Section 1.5, Basics of Factoring Polynomials, Part 7. I mentioned in the last video that those example 9C and D problems were examples of perfect square trinomials. So it's a special case of this new factoring method. Well, an additional case, a special case, is called the difference of squares. And something to keep track of and to really stress and highlight is the fact that it's a difference. That's going to mean subtraction. What this special factoring will do for us is if we recognize this pattern where we have a squared minus b squared, then the factoring of that expression is automatically the terms a plus b times a minus b. So I mentioned stressing the difference part is because the operation in between these squared pieces has to be subtraction. There is no factorization for the addition of squares. This does not give me a plus b times a plus b. We saw just in that last video that a plus b times a plus b is that perfect square trinomial, which has more terms than just these two, right? There was that middle term that we had to consider. So it's important to keep in mind that this almost like shortcut or this new rule only works when I'm subtracting two square pieces. Now, where does this rule come from? How come we end up with just the a plus b, a minus b? Well, if I think about it, looking at the factors, right? If I'm given a plus b times a minus b, and I want to know what the multiplication would result in, what would the distributive property give me? Well, I'd multiply a times a. Well, that's a squared. I would do the outside. A times negative b would be a negative ab. Then I could do the inside. Positive b times a positive a is a plus ab. And then I would do the last terms. Positive b times negative b would be a negative. Positive and a negative is a negative. And b times b is b squared. So from that distributive property, we notice that the ABs on the inside, they're the exact same thing, but one is negative and one is positive, so they end up canceling to 0, leaving behind just the a squared minus the b squared. So that's the reason why this works. That middle term is always going to cancel off when we have this particular setup. Now the square parts themselves, the a and the b, they don't necessarily have to only be numbers. They could be variables, multiple pieces of variables. So recognizing and thinking about this more as a first term that's a nice square minus a second term that's a nice square. That's when I'll be able to use this type of factorization. I will have to establish the a value because notice in the rule there's no squares on the a's, and the same thing for the b's. I'll have to break it down into an a and a b without the powers. So let's try it. Example 10, factor each expression. On part A, we have x squared minus 9. So looking different than our other examples, there's only two terms here. And I'm recognizing that I have an x squared to start, and I also have a 9. That 9 is a nice perfect square. So I'm going to try out this rule then. So my a squared is going to be that x squared part. So the a squared in my rule is the x squared here. The b squared is the 9, right? And the minus is along with the rule. So I need to know then, well, what's a and what's b by itself? Well, if I have a squared equals x squared, so it makes sense that a is equal to x. And then my b squared is 9. So what did I get? What did I use to get that 9? I used a 3, right? 3 squared gives me that 9. So then my factorization using my rule, I take my a plus b. So a is the x plus b, that's the 3, times, so my other parentheses, a minus b, so x minus 3. In other words, the a and the b are the same. The only difference is one term is positive, one term is negative, but the values are the same. And that is how we use the difference of squares. So establishing what's your a, what's your b, it's a matter of plugging in to the pattern, to the rule here. Let's try the next one. P squared minus 36. So if my p squared is the a value, the a squared value, then what is our a? It's just the value of p. And if 36 is our b squared, what's the value of b? Well, 6 squared gives me 36. Right, we're figuring out these values that we're going to use. So then we have p squared minus 36 is equal to p plus 6, a plus b, times a minus b, so p minus 6. And there's our factorization. Let's jump to the last one. Let's jump to D. It's a little different. I have r squared. Okay, we can deal with that. But then I have minus m squared. So I don't have any numbers here. But it's still a nice square, subtraction, nice square, right? It's still following the pattern of a difference of squares. So if this is my a squared, this is my b squared, my a value here, if a squared is equal to r squared, then we'll match up a with r, and then we'll do the same thing with the b. B squared is m squared, so we're going to match b and m there together. And we follow the rule. So r squared minus m squared, set up my parentheses, my r plus my m, there's my first term, r minus m, my second term. And there it is. There's my factorization. So whether we're dealing with numbers, with other variables, if that pattern is there at the very beginning, we can use this difference of squares. Let's try them a little bit more intense, we might say. Example 11. We have all kinds of mixtures of things here. So on example 11a, we're looking to factor. We have x squared minus n squared times y squared. So I have a lot of squares floating around here. It doesn't look exactly like my rule. The first part does, right? That's my a squared. That's pretty straightforward. But then my second term, it has two parts when my rule only has one. Well, by the rules of my exponents here, if I needed to, I could rewrite this n squared y squared as n times y squared. I can rewrite it in that way so that it matches the rule a little bit better. And in fact, if that's my b term, right, I can even almost, my b squared term, I should have said, I can even see what the b value will be here. So those squares, I can combine them into one term, and that's going to give me my a will just be the x, and my b here will be the n times the y, the inside part of it. So from my factorization then, we will have set up parentheses. I'll have x plus n times y, add them, and then we'll subtract them. X minus n times y. And we get our factorization. Now what about b? Part b. Ooh, it's even more complicated. I have 4 different variables, but recognizing the pattern. In my first part, they're both squared. So if I wanted to, I could write it as xy squared minus the second terms are also both squared. So again, I can write that in this way. Now you may be wondering, what happens if this was p cubed, right? What if I had a cube on that, or a third power on that p? Could I still do this? Well, would this second term be a nice perfect square? It wouldn't, right? So I would have to do other types of factoring. So again, the stressing the name of it, the shape of it, they have to be perfect squares, a and b, with a subtraction in between. And we do have that, so we're okay. And then if you want to label, your a value will be x times y, and your b is r times p. And we write in to the rule to get our answer, the factorization of that expression. So parentheses, my a value is x times y, plus my b value r times p. Then I'll do the same thing, but a subtraction in between. xy minus rp. And there it is.